Hi, today we will talk about projective spaces. So let K be a field for this. The projective n space. So we will consider the one-dimensional subspaces of Kn. So the projective n space let's denote by P and K, or simply by Pn when K is clear over K is the set of all lines in a n plus 1 through the point the point 0, 0, 0. Namely, so if we see, so we can also say that Pn is one-dimensional subspaces. Of Kn plus 1. So Kn plus 1 is an n plus one-dimensional vector space. Kn plus 1, yes. Okay, one-dimensional subspaces. So by this definition, so let's give some example first. If you take n to be 0, one-dimensional subspace of K is a Kn plus 1, in this case is K, and there is only one subspace of dimension 1, so that P0 is just a single point. So for example, if you take K to be R, there is only one subspace of dimension 1. And if n is equal to 2, so if n is equal to 1, for example, let's take K to be R again. Let's consider like that, so that we look at all lines. So in this case, the elements of the P1n are all these lines. So all these lines represent a point in the projective space. So these are points in elements of P1. Let's say R. So each one of them each one of these lines is an element in the projective space, in the projective space. Okay, next. So a line in, so if you take a point, so if, let's do it by like x, which is not 0, x1, xn plus 1 is a point in a n plus 1, then this determines a unique line, determines a line, this line, so lambda times x1, lambda times x2, lambda times xn plus 1, xn plus 1, where lambda is from the field. So that so that x1, xn plus 1, and lambda times x1 and lambda times x plus 1 determine the same point, determine the same line in an plus 1. Okay. So in fact, the points x and y determine the same line. So these are let's say in an plus 1 minus the point 0, 0. I could not write here. In an plus 1 minus 0, 0. So at least one of those coordinates of x and y is zero, as non-zero, determines the same line if and only if there exists a non-zero number in K such that xi is equal to lambda times yi for all I. Now we may define an equivalence relation on this an plus 1. So remember, an plus 1 is just the points of the vector space kn plus 1. Except 0, 0, 0. Define a relation as follows. So the point x, this x1, xn plus 1 is related to y if and only if xi is equal to lambda times yi for some lambda 0 and for all I. Okay, this is definition. So these two definitions, it's an easy exercise to check that. So I urge you to check that this is an equivalence relation. Like I started from page 7, is an equivalence relation on this an plus 1 minus 0 if and it's an equivalence relation, and the equivalence classes, let's denote the equivalence class of x1 xn plus 1 by x1 x2 xn plus 1. So these are this should be little x's, not the capital X's. So we use the capital X's for the polynomials. So for lambda is not 0. So x1, x2, xn plus 1 is the same as lambda times x1, lambda times x2, lambda times xn plus 1. So this is so that the equivalence relation, equivalence classes So each class, in fact, align so that equivalence, the set of equivalence classes of the relation this is Pn. So Pn is the set of equivalence classes. Okay. Suppose that xi is not 0. Suppose some xi is not 0, then by this star, then this set, this equivalence class x1, x2, and xn plus 1 is the same thing as x1. So if we multiply by each coordinate by 1 over xi, so it is x1 over xi, xi minus 1 over xi, and ith coordinate is 1, and then xi plus 1 over xi, and this xn plus 1 over xi, xn plus 1 over xi. Okay, so that so let's define the set as ui to be these equivalence classes x1, xn plus 1, such that xi is not 0. So that we can also take that coordinate to be 1, so that it also can be defined as like this x1 up to xi minus 1, and you can take the ith coordinate to be 1, xi plus 1, and then up to xn plus 1. So these xi's are these x1 over xi's of the previous equality. So such that xj's are in K. So here, of course, all the xi's are in K. Okay. So, for example, let me give one example. Or let's take K to be R. N to be 1. Then we have U0 and U1. So let's see what's U0. Sorry, not U0, U1, U2, sorry. We have U1 and U2. So these UIs are defined for i's from what here is I is 1, 2, up to n plus 1. So U1 is 1, and the second coordinate is x2, such that x2 is R in R. And these are, if you think of these are the lines, of course, whose first coordinate is 1. So this is let's see. Also, let's write U2. U2 is, remember, now we can take the second coordinate to be 1. such that x1 is in R. Let's see. So if so here for U1, the first coordinate is taken to be 1, so that all the points on this the line x is equal to 1, so that all these lines. So all the lines except y-axis. So this way we get all the lines except y-axis, except this. So let me choose except this, this red line. This is U1, and U2 is, the second coordinate is 1, and let me say except the line, this x-axis. We take all the lines whose first, we're passing through the 1x2. 1x2 is, so x1 and 2, x1 and 1, sorry. So this is the line y is equal to 1, x2 is equal to 1, so that you take all the lines passing through those points. So all these lines, they should all pass through the origin, of course. All these lines, except the x-axis. So that, so for example, for U1, U1 intersection, so U1 union U2, I was going to write with this color. U1 union U2 is P1, RP1, P1, or we also call RP1. And their intersection is U1 intersection U2 is all x and y such that x is not 0, y is not 0. So that all the lines except the x-axis and y-axis. And P1 minus U1, for example, is just 1 point, and that's y-axis. It's just 1 point. And P1 minus U2 is the set everything, all the subspaces except the x-axis. Except x-axis. Okay, so we may see this as a circle. So RP1 is, we can see RP1 as RP1. Each point in P2, RP1, I mean P1 or P1R. We also call this RP1, another RP1, common notation. Okay, so these are, so for any line, so if you take any point on this, if you take any point on this unit circle, any point determines a line, determines a subspace, namely it determines a point in the projective space. But if this point is z, for example, that point is minus z, they represent the same point. They represent the same point, so that we can see this as. But if you just take this upper half space, upper half circle, then every point represents a unique line in the projective space, except these endpoints. Endpoints represent the same line, so that P1R is just topologically, it's just a circle. If you know topology, it's just a circle. Namely, what you do is that, so this is each point of this upper half circle determines a line, determines a point in the projective space, and each projective space determines a point on the circle. And these endpoints represent the same point in the projective space. So if you glue this point to that point, you get a circle. So that there's a topology on this P1R. With that topology, P1R is homeomorphic to circle, which we will not go into that. We will be interested in the algebraic structure of this projective spaces. Okay, and similarly for RP2, P2. So let's look at n is equal to 2. So when n is equal to 1, this P1 K is called the projective line. Projective line. And for n is equal to 2, let's take again K to be R. In this case, P2 is this, the lines, one-dimensional subspaces, in R3, so that the lines through the origin in this case, just as above, if you consider this this upper half, the upper half of the sphere, each, if you take a line, one-dimensional subspace of this R3, then it will determine a point on the circle. For example, if you take this line, it will determine that point. If you take this line, for example, it will determine that point in the circle. So any point in other than any line which does not lie in the XY plane represents a unique point in this upper half space, upper half circle, sorry. But on this upper half circle, so if you take any line in the XY plane, then it will represent this. It will intersect this. Circle, boundary circle, at 2 points, so that these 2 points represent the same point, so that we can see RP2 as P2R as all the lines, or this this hemisphere, but these antipodal points on the boundary are identified. So we represent it like this. We say it like that, denoted this way, so that this side is identified with that side. So this point is glued to that point. So it is not embedded in, you cannot see it inside R3. Okay, that's the projective. Oh, by the way, this P2K is called the projective plane. And this is called the real projective plane, of course. This upper hemisphere, but you identify this antipodal points, so the opposite points on the boundary. Okay. Now, if after this, let me change this pen to continue. So if P is equal to, let's say, x1, xn plus 1 is a point in the projective space. This x1, x1, xn plus 1 are called homogeneous coordinates. Of P. And remember, this point P can also be represented like this. P is also is equal to, it can also be represented like this, x1, not the same x1, let's write x1, yeah, okay, x1, and it is xn minus 1, 1, and if you represent it like that, and then xn plus 1, not n plus 1, I plus 1, if you represent it like this, then this x1, xi minus 1, these n points, n tuple, xi plus 1, and xn plus 1 is called non-homogeneous coordinates. Non-homogeneous coordinates. Okay, that's the non-homogeneous coordinates. Now, let's define a function. Phi I for each, of course, for I is equal to 1 to up to n plus 1. Let's define a function from an into ui, where phi I of a1 an as just a1 I minus 1, and remember the ith coordinate of the point in ui must be non-zero, so we can take it to be 1 ai, so that an, so that here we have n plus 1 coordinates in this here. This phi I is 1 to 1, 1 to 1 and on to. You can check this. And Pn is U1 union U2 union Un plus 1. So let's check one example. Let's take n to be 2 again. N to be 2. Remember, U1 is this. So let's consider U1. U1 is first coordinate is 1, second coordinate is x2. So this set, so that these all these lines except x-axis, as we saw above. This is all the lines. Except the x-axis, so that if you consider this part to be a r, so there is a function from r to the function phi I from r to the projective space is this point goes to that line. The point in r, so if you take remember, as you see above, so if you take a point, let's say A in R, so this is the point A in R, so you look at the line passing through 1 and A, and the origin, of course. So that's the one-to-one map, and so let H infinity is Pn minus Un plus 1. So for n is equal to 2, so this is n. Okay. Okay. Yes. So that is this is the set of, remember, un plus 1 is the set of points where the n plus first coordinate is non-zero. So its complement is x1, x2, xn, and the last coordinate is 0. So the xi's are in K. So this is the, so this H infinity is called the hyperplane at infinity. Infinity, and and H infinity is, if you forget about the last coordinate, if you forget about the last coordinate of the zeroth coordinate in H infinity, so you can define a map from H infinity to Pn minus 1. Pn minus 1, mapping x1, xn, and the last coordinate is 0 to the point x1, xn. And just forget about 0. So this is a bijection. This is a bijection, 1 to 1 and onto. So that therefore, our Pn is H infinity, and H infinity is union. Remember, this is n plus 1. This is disjoint union, and this H infinity is also Pn minus 1 union un plus 1. Okay. Okay. Do I have anything else to say about this projective spaces? So I already gave examples. Yeah, this is, yeah, one thing. So here is example. Example. So let's consider the line. The line y is equal to mx plus b in A2. So identify A2 with U3. So remember U3, there's a bijection between A2 and U3. In fact, because of the topology, there's a homeomorphism. So U3, remember, what's the U3? U3, all those points, all these lines where the z coordinate is not 0, last coordinate is not 0, so that this is U3 is in fact all the lines through origin through 0, 0. Of course, 0, 0, and which is not in the XY plane. Not lying in the XY plane. So in our representative above, so remember we denoted the RP P2 is like this. So this is, in this case, U3 will be this, everything in this hemisphere except this boundary point. Except this boundary point. So this boundary point will represent H infinity. And this upper hemisphere, except this boundary, represents U3. Okay. So if when we identify this A3 with U2, then this the points in U2. So remember what's U2? So what was the map? We had the map from A2 into U3, mapping XY into XY 1. So let's think it like that. So that's the map. So that this line maps to, this line corresponds to, so XYZ in, so X, the point XY 1, XY 1. So let X, the point correspond to sorry, what do I want to say? What do I want to say? Okay, let me say it like this. So the points in U3 are like, we can also say it like that, such that Z is not 0, such that Z is not 0. So that if you, so we can, so this Y is equal to AX MX plus Y is equal to MX plus B corresponds to, so Y is equal to MX plus BZ, where Z is not 0. How does it correspond? More precisely, think it like that. So in this Z is equal to 1 plane. So if you have a line like that, then you look at the plane, all the lines containing, you look at all the lines passing through these points of this line. So that is this equation is, the equation of this plane is Y is equal to MX plus BZ. Okay, MX plus BZ. And this plane in P3, R3, that represent plane P3 represents a line in P2, and so let me just finish here. I will continue this later. Okay, my time is up almost, so let me finish it here.